Archiving started.
Okay, go ahead. Yeah, it looks like Kimoni is trying the telephone.
Yes, I think I'm here now.
Okay, yeah, I can hear you.
Okay.
Go ahead.
It's my first time using it. I've never. Oh, it's only one person that can talk at a time?
I think so. Yeah. It is so that the participants can only talk when they push down the talk button. But I don't know if several people could talk at once or not. With the phone, you might be able to talk all the time.
Oh, okay. Oh, no, that's fine. Let Margina Wood go ahead because she was in here first.
Okay,
I was just trying to set it up to figure out how to use it, but now that I know, she can go ahead.
Yeah, it takes a little while.
Okay.
Okay, so that's the expansion lab. Okay, yeah, let me open up to that page. And I'm also going to start the e-board where we can type things out. Okay. We can probably use the example for the spectrum that is given on page 25.7. And it's actually an example of what the spectrometer would read for a galaxy in terms of the absorption lines and also in terms of the apparent magnitude. So let's do that. I'm going to copy that over here, and I'm just going to start typing, how to calculate the distance. That's basically what we want to start with. So how to calculate the distance of the galaxies in Data Table 1. Okay. And essentially, the data that we're given from the spectrometer, so the spectrometer returns the apparent magnitude. Let me just write that out. So the spectrometer of the telescope gives the apparent magnitude, and the wavelength of the calcium K and H absorption line. And then in our example from page 25.7, so the example, the sample spectrum from page 25.7 gives the following. So I'm going to change the color to blue. So we get M for the apparent magnitude equal to 12.3. And the wavelength for the absorption lines, so lambda for the calcium K line okay, well actually I'm showing the example for the calcium H line, but we can estimate something. Maybe something like 4,012 angstroms. We have to estimate that because the figure shows how the wavelength is measured of the calcium H line. And the lambda for the calcium H line is actually given or measured as 4047, so 4,047 angstrom. Okay, and then, but the first thing we want to do for the data table is calculate the distance. Okay, so first, calculate the distance for the data table 1. And we're going to use the distance modulus formula that we've also used for in classification, we use them once to calculate the distance of the stars and then figure out if they're in the Milky Way or not. And then we use them for the Pleiades lab, to calculate the distance of the Pleiades cluster. So the distance modulus formula. I'm going to put that into the new line where D is equal to 10, and then we have sort of a complicated exponent, 10 to the 2 parentheses open, lowercase magnitude, which is the apparent magnitude, minus the absolute magnitude, plus 5, first parenthesis closed, and divided by 5, and then the second parenthesis closed. And then we assume that the galaxies we measure are the brightest ones in their cluster or at that distance for, for the Hubble, for the expansion lab, we get 6 different galaxy fields. And, we assume the only reason we see one galaxy field dimmer than the other or smaller than the other is that those are a lot further away, but that their intrinsic brightness is about the same. So, also, for all galaxies, we assume an absolute magnitude of, this is now the absolute magnitude of an entire galaxy were 10 kiloparsecs away from us. And of course, that would be like immensely bright. So it's negative 22. We'll calculate the exponent first, and then raise the 10 base 10 to that power. So the exponent alone, maybe I'll put that on the next slide. Yeah, let me just save this. Well, let me just say start with the exponent. So the exponent alone would just be apparent magnitude minus absolute magnitude plus 5, parenthesis closed, divided by 5. We can actually calculate that here. So I'm just going to change my pen color. Okay, so we're going to get the apparent magnitude that was measured by the spectrometer. That was 12.3 minus, and now we have negative 22, so that's a double minus sign, plus 5 divided by 5. So what will the numerator be? Let's see, 12.3 plus 22, that would essentially be 34.3 plus 5, 39.3. So 39.3 divided by 5. See, I'm trying to do this in my head, so if I'm making any mistakes, please correct me. Maybe I should bring up a little pocket calculator here on my screen, just to be sure. So we have 12.3, and then negative times negative is going to give us plus. So plus 22 plus 5. So that's 39.3, and that divided by 5. So 7.86. Let me just write out the 39.3. Oops, I have to change over again. 39.3 divided by 5. So I'll just put the result on the next slide. I'm going to save this one and clear the slide. Okay, so the whoa comes in a much bigger type. See, I don't know how to get the writing smaller. Well, at any rate, so the exponent equals so 39.3 divided by 5, 7.86. I'm going to switch this over again. Okay, 7.86. And that's just a number because it is the exponent. Now for the distance, we use that exponent for the base 10. So let me just go back to green. So for the distance, we're going to use the exponent for the base 10. So that would be d is equal to 10 to the 7.86 power. And then if someone could maybe calculate that, because my little computer calculator here doesn't do exponents. Well, it should be on the order of, well, 10 to the 7, between 10 to the 7 and 10 to the 8. Yeah, so 1, counting the digits here. Okay, that's 6, 7. Yes, and it's closer to, so we have, yes, 72 million parsecs. So the distance, this formula generates the distance in parsecs. Okay, so we have 72,443. Well, you know what? We only use 3 digits for our exponent, and the result technically, I know we didn't talk about this in class, but the result technically cannot be more accurate in terms of how many digits it has than, you know, the least accurate value that went into the calculation. So we're just going to go with 72,400,000. So we rounded that a little bit. So that's in units of parsecs. That goes into the the fourth column, distance in parsecs. And let me put that in a different color behind it. So that's the fourth column. And this writing is just so large. Okay, the fourth. Okay, and then we're going to calculate the distance in megaparsecs, which is the fifth column. Okay, and the abbreviation of megaparsec would be a capital M and then lowercase pc for the parsec. Now, mega is a prefix, and I don't know if you remember what it stands for. See, the prefix mega stands for 10 to the 6th. So that means if we go to our number, which is 72,400,000, if we convert our number to scientific notation, then we will get something like, and if we convert it into scientific notation such that we keep the power of 6 as the exponent of the 10, then we'll get 72.4 times 10 to the 6 parsec for our distance. So in other words, we can, oh, wait a minute. Okay, yeah, maybe we didn't go over that. And then we can just take the 10 to the 6th and replace it with the capital letter M, because the 10 to the 6th is equal to mega. So we get 72.4 megaparsecs for the distance. And this is what you would write as your result into the 5th column. Okay, so that's how you get the distance. Now we also need to calculate the average velocity with which the galaxy moves away from us. And this we do with the measurement of the wavelength, because eventually we want to plot, oh, you said why 72.4? Okay, yeah, let me show you how I move the decimal point here. Here, let me go back to green. Because we're going to move the decimal point to convert to scientific, oh, that's blue, notation. Okay, hang on. Yeah, basically you start with 72,400,000 parsecs, and to convert it to scientific notation. Let's see, let me change my pen color. Yeah, since we have an integer number, so that it's not like point something, we just put the decimal point here at the end of the number. And then normally when we would convert it into scientific notation, we would move the decimal point as many times as it takes to get just one digit in front of the decimal point. But because we're looking for a factor of 10 to the 6th, we want to just move it by 6 places. So, see, 1, 2, 3, 4, 5, 6. Okay, so we're moving it by 6 places. Let me write a 6 underneath. Okay, so that's in red, so it's moved by 6 places. So we'll get 72.4, and then the rest, so the number of spaces by which we have moved the decimal point is then absorbed into the power of 10. And 10 to the 6th is essentially 1 million. Because we could get our 72,400,000 back by multiplying, the 10 to the 6th, turning that into 1 million, and then multiplying 72.4 times 1 million. So then we would get our 72,400,000 parsecs back. But because we wanted to use prefixes, we pulled the factor of 1 million out and expressed it as a power of 10. And, you know, just like the prefix m mega being equal to 10 to the 6th, that's just like the prefix kilo being equal to 10 to the 3. So that's just sort of a convention that everybody has agreed on. So let me just write that, add that up here. Okay. Okay, does it make a little bit more sense? Okay, great. So the second calculation for the data table is calculating the average velocity with which the galaxy moves away. So save the slide. Now I'm going to erase it again. Okay, so now we're calculating the average velocity. Let me call it recessional velocity because that is the velocity with which the galaxy moves away from us. Of the galaxy by using the redshifted calcium K and calcium H lines. Okay, so the lines from the galaxy, let me write that in red because it's redshifted. Okay, so the lines from the galaxy have the following wavelengths. So we had said that lambda for the K line was equal to 4012 angstrom. Maybe I'll just abbreviate that as A. And lambda H was 4047. Let me just double check that. Yep. Okay. So those would be the lines from the galaxy. Actually, I can put the lines from the regular lines in the laboratory next to it in a different color. Yeah, let's do it in green. Okay, so in the laboratory, or here on Earth, so from a sample of calcium that is not moving, we get for the K line, let's see, I'm wondering if I should draw that by hand, but that may make things worse. Okay, let me just say that the K line, I have to look that up in the book now. Here they are. (3933.67) for the K line. And I'm just going to use this A as a unit, and the H line, okay, so 3933.67 for the K line, and 3968, well, I'm going to round that, 0.85, 3968.85. For the H line. Okay, and you can really see with the values, you know, in the laboratory, if we just have calcium, you know, we heat it up to the point as a dilute gas. Well, actually, we have to put a black body spectrum through it and then have it as a cool gas. But the absorption lines come in at 3,900 angstrom essentially, or just above 3,900. And, you know, the same element in the galaxies that are moving away from us come in redshifted at slightly over 4,000 angstroms. So based on this stretching of those particular calcium lines, we can then calculate by how much, you know, how much the shift is, and then how much the shift is directly proportional to how fast it is moving away. Well, actually, that's what we want to find out when we graph the whole thing. So for now, we can calculate the speed using the shift. Actually, yeah, let's calculate the shift first, and then we can do the speed on the next page. Okay, so the Doppler shift of the K and H lines is essentially just the difference. So we just subtract the two. And that is delta lambda. So delta lambda K is equal to, and it's always the shifted minus the laboratory line. Yeah, I just checked. Lambda K goes into data column 1, 2, 3, 4, 5, 6, and the H line goes into 7. Yeah, that's what you would get from the experiment. Yeah, let me just write this in freehand. Because I forgot about that. So okay, so the lambda K wavelength goes into data column 6. Looks like a B. And the H wavelength goes into column 7. Oh, that doesn't look like a 7 at all. Oh no, it took everything away. Oh shoot, I pressed the wrong button. Now I've done it. Okay, let me just quickly try to type it up again. Okay, so we just going to type this up real quick. Okay. So actually, let me put it right here. So we have lambda k was 4012 angstrom. Okay, and now I can write in parentheses that goes into column 6, and everybody will be able to actually read it. And lambda h, which was 47 angstroms, goes into column 7. Okay, and then we have, well, what we're going to do, we're going to calculate the shift. So we're going to calculate the shift delta lambda by subtracting the unshifted wavelength. Okay, and I'm just going to write those out. So for the unshifted lambda k was equal to 3933 0.67 angstrom, and for the K line we get 3968.85. Okay, 3968.85 angstrom. Okay, so then the shift actually, let me do that in blue then. Okay, so that would be the K shift would be measured minus the unshifted wavelength from the laboratory, so 4012 minus 39.33, 33.67, and that comes out to be okay, so 4012 minus 3933.67 equals 78.33 angstrom. Okay, 78.33 angstrom. And then for the shift of the H line, we get 4047 minus 3968.85. So 4047 minus 3968.85 68.85, and that equals 78.15. Okay, so 78.15 angstrom. Okay, let me save this before I accidentally clear everything again. Okay, so those are our wavelength shifts. So the calcium K line has stretched by 78.33 angstrom based on the speed with which the galaxy is moving away from us, and the H line has stretched, well, from our measurement by 78.15. Now, both of these lines come from the same galaxy, so the whole thing is moving away with a certain speed, so we should get that speed from every single wavelength we measure. So ideally, the shift from every absorption line would be exactly the same. But of course, we're dealing with an experiment, even though it's simulated. But in every experiment, there's a little bit of noise, a little bit of experimental error involved that has to do with the apparatus or the viewing conditions, something that is beyond human control. And that's why there's a little bit of variation in the experimental values that we get. That's why we wind up taking the average, because taking the average of two values is actually sort of cutting down on the overall error. And if we had 5 absorption lines and we would take the average of those 5, then we would even get less of an error. So that's why we're actually measuring 2 absorption lines instead of just 1, so that our result of the speed can then be more accurate. Okay, so let me clear this slide now, and we're going to go ahead and calculate the recessional velocity. Okay, now, oh, wait a minute. Oops. My slide doesn't want to clear. Now I want to clear and it doesn't cooperate. I saved it. I just saved it again. Okay, here we go. Maybe I was just talking too long. So we're going to use the Doppler formula for the recessional velocity. For the galaxy's velocity. Okay, and the Doppler formula, I'm going to write that offset a little bit. Okay, so that's V is equal to the speed of light, which is c, times delta lambda, which is the shift, and then divided by the original or rest wavelength. Let me just write unshifted. Let me abbreviate that. Unshifted wavelength, because it won't fit. Okay, and where c is the speed of light, and it doesn't really matter if you use units of meters or kilometers for the speed of light. Whatever unit you use, that will also be the, kilometers per second or meters per second. So whatever unit you use for the speed of light, that will then also be the speed unit for the recessional velocity. Let's see what number we'll be using here. Okay, well, we're putting a graph. Okay, so we're graphing distance in megaparsecs on the horizontal axis, and then velocity in kilometers per second on the vertical axis. So that means we want the speed of light in kilometers per second. And that's going to be 3 times 10 to the 5 kilometers per second. I think the lab manual, I meant to fix that, has us calculate, the speed for the K line and then calculate the speed for the H line and then take the average. But actually it would be more efficient and just as accurate if we were taking the average of the two wavelengths and then just calculate the average speed from that. But since we're following the lab manual, that's going to be in the next edition. Streamline it a little bit. But let's go ahead and calculate the speed from the K line. So the K speed is going to be C times, and then, what was it, 78.5, oh, no, there was the second one. See if anybody can refresh my memory. What was the shift we calculated for the K line? Yeah, you can just type it in. Let's see, maybe I can reproduce it. See, we have 40, 12 minus 3933.67. Okay. 4012, I'm typing it into my little calculator here on the screen. Minus 3933.67. Okay, 78.33. That was the shift from our K line. So 78.33 angstroms divided by the unshifted wavelength, which was 3933.67 angstroms. And you see, well, let's see, as soon as I switch over here, I calculate, C was 3 times 10 to the 5. I should have written that out. Let me just make an arrow here. Okay, now I'm clicking the right button. Okay. Okay, so that number goes right there. So then we have 78.33 times, actually, let's start this new. 78.33 times 3, 2, 5 zeros for 300,000 kilometers per second, and divide that by 3933.67. Okay, and that's going to give us an average, a speed for the K line of 5,974. I'm just going to round it there. 5,974, and the unit would be kilometers per second. Okay, and then we're going to repeat the same calculation for the H line. Okay, I think I'm going to have to let my dog in. He's desperately trying to get in. Hang on. Oh, he's trying to play now. Playing with toys. Okay. So let me type out the 3 times 10 to the 5, and I'm going to not do the units or we'll run out of space. And that was 78.15 divided by, let's see, 3968 0.85, and that's gonna, let's see, let me quickly go ahead and calculate that. So 300,000, because my calculator is not very sophisticated here in the computer, times 78.15. Okay, the heavy breathing in the background is the dog, okay? Divided by 3968.85. Okay, and here we're going to get 5,907. So let me switch that back here. Okay, 5,907 kilometers per second. Okay. Okay, my board is frozen up again. I'll change color here, maybe that'll resolve it. Okay, let me start typing. I just typed an entire line and it hasn't appeared yet. Anyway, let me give you the column numbers that those go into. So VK goes into column, wait a minute. Yeah, VK goes into column 8. Oops. And VH into column 9. And, okay, so apparently it just totally deleted the line that I was typing. Let me just retype it about how to calculate the VH. So you have 3.3 times 10 to the 5 times 78.15 divided by 3968.85, and that was 4,000, what was it, 5,907 kilometers per second. Okay, no, unfortunately that wound up being green now. Okay, well, let's calculate the average. That goes into column 10. Okay, in general, the average is calculated by adding up the experimental numbers you have divided by how many numbers you have. So in our example, we just had 2 experimental numbers. So we add those up and then divide by 2. So 5,974 angstrom plus 5,907 angstrom divided by 2. Okay, and now I'm going to use my little calculator here. 5,974 plus 5,907 and divide the sum by 2. 5,940.5. Okay, so we get 5,940.5 angstrom is our average velocity. Okay, I'm going to save this slide. Okay, so you would do this procedure for the values of the 6 galaxies. So from each galaxy, you just measure one, from each galaxy field, you just measure one galaxy in the program and then go to the next galaxy field and pick just one galaxy there. And you will get different amounts of redshift and different distances. Now the graph has already a template, so it has already tick marks on it that go with the size of the numbers that we have calculated. Yeah, maybe I can just quickly go ahead and sketch the diagram, or sketch the graph. I think I saved this, just to be sure. Clear the slide, and okay, I'm just going to call that how to plot the speed. Actually, I've called it velocity, so let me be consistent, versus distance. Actually, I should make it a little bit smaller. Okay, so here on the vertical axis we have velocity, and on the horizontal axis we have the distance. Distance was in megaparsecs, and the velocity was in kilometers per second. Okay, and then, let me make some ticks. Switch pens again. I'll try to space them evenly, but I don't know how well this comes out, so I'm doing this by freehand. 1, 2, 3, 4, 5, and then the speeds given here are 10,000, 20,000, 30,000, 40,000, and 50,000. I don't know how well those numbers are going to fit on the screen here. Let's see. That's still just as large. Let me just write just 10 th for 10,000. 20,000. 30,000, and then you just have to imagine it keeps going up, 40,000, 50,000, or it'll become really cluttered. Let's see, and then the tick marks on the megaparsecs are 1, 2, 3, 4, 5, 6. So you have 1, 2, 2, 3. I should have picked the straight line and not the freehand. You live and you learn. 4. Well, we don't need the entire range. Okay, and then, the numbers were in hundreds. So we have huge numbers now. 100, 200, 300, 400, making it a little bit up and down so we can actually tell that it's not just one giant number. Okay, 500. And the coordinates for our point were, I'm going to make those different colors. So the distance for our galaxy what have we calculated there? 72.4 or 74.2? Does anybody remember? 72.4. Okay, thanks. 72.4 megaparsecs. MDC. Okay, and the velocity, which I'm going to abbreviate because otherwise it's not going to fit. It's going to be 5,040.5. kilometers per second. Okay, so plotting that, actually, we probably calculated the velocity of a galaxy that is still pretty close by. Because essentially our velocity would be right here. Okay, we do this, roughly in the middle there. Probably to about here. And then down to about here. So our point and now it's coming up with a thinner line. Yeah, I selected a thinner line. Let me just undo that and redo it with a thicker line. Because I was trying to get the writing to be thinner, but apparently that didn't work out. Okay. Onto straight line. A little bit lower. Okay, so our data point would be right here. Okay. And then, so this would be for the closest galaxy. And then there will be other data points that you get. So I'm going to put in some sample points now with green. And, well, maybe what we can do before we jump off is just go ahead and calculate the slope. Because the slope is the answer for question, well, actually E under calculations. So that's going to finish up that part of it, and then, yeah, maybe we can discuss the rest by email. It's just going to be calculations, but yeah, seeing the graph done is probably pretty important as a visual. Okay, so I'm just going to put in some example points in green. Sounds like my dog is getting ready to bark. That are not part of the data set. So whatever I draw in green, you probably won't be getting the exact same values when you measure the other galaxies. I'm just putting them in so I can demonstrate how to calculate the slope. So let's put one in. Oh, gotta switch my pen again. Oops, oh, went a little bit too far. Put one here. Freehand thing's not so easy. And then maybe another one. In here. Okay, yeah, that looks a little bit scraggly. So when we now plot the line, we're looking for a best fit line that comes closest to all of the data points, but without connecting the data points. So that's pretty important. because each data point has a certain amount of experimental error in it. And I had already mentioned that when we talked about why we were taking the average of 2 lines. So it comes from instrumentation, it comes from viewing conditions. So anything that is beyond human error, that we could possibly take into account, just the experimental conditions. So if we were connecting the lines, we would get some sort of a zigzag going that wouldn't conform to any physical law in nature. So by taking a ruler and drawing a straight best fit line, we're actually averaging out the error that is in each of the data points, and any point on the line will be more accurate than any of the data points. And then we can read any point on the line for our slope calculation. Okay, so I'm going to use, let me use purple for the best fit line. And I'm going to use a straight line tool now. And we're starting at 0. Well, okay, let's go too early. Yeah, maybe something like this. Then any point on the line we pick will be more accurate than taking any 2 data points and calculating the slope from those. So let me just go ahead and pick my point here, since we have 0, 0 as one of our points, meaning that our own galaxy is not receding from us, and it's also at a 0 distance from us. So this curve or this graph has to go through the 0, 0 point. Okay, I'm just going to take, let me take, yellows might be hard to see. I'm going to use teal. Okay, so I'm just going to pick my 40,000 mark here. See where that intersects. Trying to get this straight. Okay. And go straight down. And it's not entirely straight. Okay. So then the slope put that over here. Y is over 1. So that would be 40,000 divided by, well, I'm just going to estimate that as 410 megaparsecs. Now let me just divide the numbers. That'll become too messy here. And do it on the calculator. It's probably over 90, so that's a little bit large. In the experiment, you should get something around 75. Yeah, this is going to be 97.5, which is a little bit high. But since we're just doing this by example, to show you the technique, would be kilometers per second per megaparsec. I'm going to just put the megaparsecs also in the denominator, and I'm going to make a note here that so this is, or you will get that the experimental value will be different. Okay, let me just okay, so this is your H, the Hubble constant, and that's the answer to question or step E on page 25-9. Okay, let me just make a quick note of that. And actually, it's already way past bedtime for my kids, so I'm gonna have to jump off then. Yeah, let me just make a quick note. Freehand. Okay, so that's the. Wish I could change the font size here, but apparently not. Oh no, it's gonna. I'm just gonna write here answer for so let's answer for step E. Hope that makes sense now. Okay. Yes, have a good night. And let's see, Jennifer, I never got to any of your questions. What kind of questions did you have? Okay, well, we'll have another chat session on Friday, or in the meantime, you can just go ahead and email me. I'm sorry I didn't get to that. It just takes such a long time to walk through calculations. Let's see, you're in the 1010 class, or are you also in the 1020 class? Oh, okay. Okay, well then, yeah, you're, at least you could see that. Yeah, so maybe any questions that I couldn't answer, just bring them to Friday or email them to me in iCollege. All right, I'm going to stop the archive now and wish everyone a good night.